Polarisation is a really new idea, and it's very, very interesting. Transverse waves are special because they oscillate at 90 degrees to the direction of travel. It's important to remember that when you have two things at 90 degrees to each other, there is actually an infinite number of different angles and an infinite number of different arrangements that you could take whilst those things are still at 90 degrees. Three-dimensional space is cool. Polarisation relies on this. Polaroid, the same stuff that you get in sunglasses or even cameras, it takes light and only allows one direction of oscillation to pass through. A polarised wave only has one plane of oscillation. If you're asked to explain polarisation, describe what is meant by polarisation, you say this: a polarised wave only has one plane of oscillation. We're talking about the horizontal plane, the vertical plane, that kind of thing. Longitudinal waves cannot be polarised, and there's only one way in which my finger and my thumb can be pointing in the same direction. I can't filter out a component of those oscillations. Whereas if they are pointing at 90 degrees, we've got all these different options. Polarisation is a phenomenon that is unique to transverse waves. And you will be asked to identify whether a wave is transverse or longitudinal based on this fact. Can it be polarised? Can it not? I've got a separate little setup over in the corner here to demonstrate polarisation to you. Polaroids is the same stuff that you get in some sunglasses. It's a bit dull on its own. It's darker because it's only letting one component of the light pass through, the light in, say, the vertical direction. You can never really tell. I've got another piece of polarizer set up down here. Where it's really interesting is what happens when you put two polarizers together. Because if only vertically polarized light is getting through this one, what happens if I run it through a horizontal polarizer? So here they are in alignment. If I turn it around through 90 degrees, they're in 90 degree alignment. As you can see, no light is being transmitted through. You can't see my little question mark drawing anymore. The first polarizer only allows the vertical component through. How do we know it's a vertical component? It doesn't matter. In this case, if you look at where the arrow is, we just call it the vertical component. It only allows that one direction through. When the second polarizer is added into the situation, it only lets the horizontal components through. But the light's polarised in the vertical plane, so it doesn't have a component in the horizontal. When it's in the same transmission axis, the vertical component goes through here and can still be transmitted through to the other side of the screen. So you can see my fingers through it that way, but if I turn it around, you can't see my fingers through it anymore. After doing components in mechanics, this is quite straightforward, I think. Anything with a purely horizontal component has no vertical component, and vice versa. That's exactly what's going on here with the light. Where you really start to understand how this works, and this kind of component-wise nature of light. If I take a third polarizer, and I put it at 45 degrees in between, so hopefully you can see this is going between the two existing Polaroids at 45 degrees, and now you can see some light transmitted through that Polaroid. It's completely opaque. Some light is transmitted. It's dark, but just about. See the question mark on the other side now. Nothing. Question mark. With this three polarizer scenario, we start off by saying the exact same thing. The observer would see some transmission. The first polarizer only lets the vertical component through. Now, that much is the same as before. However, the middle polarizer allows some light through. Vertical polarized light does have a component at 45 degrees to the vertical. So some light is transmitted through this middle polarizer. And that light is kind of 45 degree polarized, if you like. That does have some component in this final polarizer here. And so there is some transmission of light through those three polarizers. Read that standard answer back to yourself and check that it makes sense. This is talking about the component-wise nature of light, which is a bit unexpected, but very important. And again, this is unique to transverse waves.
Really interesting fact about polarized light is that reflected light is plane polarized. So if I hold my polarizer up here, you can see the reflection. If I twist it, the reflection goes away. And you can do that on anything. So if you have a look at the car park out here, if I zoom in on that, the reflected light from that disappears and dies off as I rotate even a single polarizer.
It's a really, really interesting effect, and I'll be honest with you guys, it's one that I'd never seen until I first started teaching 6 years ago. I thought that polarisation was dead easy, and it was just, oh yeah, 90 degrees is there, and the other one is not. But actually, it's way more complicated than that. We learned that light can have components of transmission, and this is a property that is only the case for transverse waves.